Okay, I'm going to be talking about blockchain, in particular, some of the specifics that Bitcoin uses. Blockchain is a more general concept that exists in many forms. There are many different cryptocurrencies, and beyond cryptocurrencies, it can be used for things like timestamping and proof of freshness. So let's start with the definition. What is a blockchain besides a buzzword? It's a growing list of records that are called blocks that are linked using cryptography. So it's essentially a linked list, but plus crypto. One of the important things about a blockchain is that you can't modify. One of the important things about blockchain is that you can't modify data that's already been written to the blockchain and propagated throughout the network of participants. And you achieve that via crypto. There are various uses for blockchain. Timestamping, so proving that some data existed at or before a certain time. Currency is probably the most well-known use case in Bitcoin, all the other cryptocurrencies. Proof of freshness means that you can show that you included something in data that existed after a certain time. That can be useful for if you take a signature on some data and you include what is considered fresh data like newspaper headlines or a block hash in a blockchain. You can show that some data only existed or the signature was created after a certain point in time, and that can be useful in some places like warrant canaries or essentially anytime you want to prove that a signature was recently created. No. So I'll get into why you can't modify. So someone asked what the reason you can't modify the data is, and it's not because the pointers are encrypted. Everyone can usually traverse the blockchain. Well, not okay. So there are various mechanisms for preventing blockchains from being retroactively modified, and we'll cover the one that Bitcoin uses a bit later. Someone asked about non-fungible tokens. NFTs are backed by blockchain technology. So the last point in this list of use cases is just anything that requires keeping a publicly agreed upon set of records that you don't want to be altered. And NFTs would make use of that. In fact, you can put arbitrary data into the Bitcoin blockchain. It can just be expensive to put large amounts of data. So in the case of NFTs, you want to keep a transaction history, which is essentially what Bitcoin is for. Although I don't think NFTs are backed by the Bitcoin blockchain, usually. So start with some review over crypto. Cryptography.
Did his sound go out for everyone else?
Preimage resistance is when given a hash, you are unable to find an input.
Soham, we didn't hear the first bullet. You kind of
That
cut
results
out.
in that hash. Oh.
I think you're still cutting out, actually. Or Majesty.
Yeah, I hear it too.
Okay, am I back now?
Yes.
Okay. This might happen a few times, depending on whether or not my broadband provider decides
Oh no.
to deliver packets, or if it's not feeling like it. So we shall see. Okay, so the first bullet point was hash functions take just the definition of a hash function. They take any length of input and they output some fixed number of bytes. So there are 3 requirements for cryptographic hash functions.
It always ends like immediately when he finishes a sentence too.
Means it's difficult to find any 2 inputs that result in the same output, which when you have 2 inputs that result in the same output, that's called a collision. Merkle trees
Sorry,
are...
can you go over
Can I go over which one?
second preimage resistance?
Right, so second preimage resistance is sort of a blend between, or second preimages are sort of a blend between collisions and preimages. So when you have collisions, you can take the goal is to find any 2 inputs that you were given one input, and the objective is to find. Essentially, the collision resistance, finding collisions is much easier because of the birthday problem, where because you can adjust both inputs. It's the search space is the square root of the total number of bytes in the digest. Whereas for second preimage resistance, I think it's still the number of bytes in the digest in terms of search space. Essentially, you're fixing one of the variables for second preimage resistance, which makes it harder. Does that make sense?
Yeah.
Okay. Merkle trees. So Bitcoin involves taking a lot of hashes in a lot of different places. If you have pieces of independent data, how do you create a single hash that allows you to validate data, any piece of data? So essentially, the problem is similar to if you have many files and you want a single hash to validate all of those files. So the reason you would want that is because the single hash is relatively small in size, whereas transmitting the hashes of every single file requires much more storage, and that grows with the number of files that you want to hash. So there is one way of doing this where you simply just hash every single file or item. They're interchangeable here. And you concatenate all those hashes, and then you take a hash of that. And then the only thing you have to trust is the hash of all the hashes concatenated. The problem is to verify that, you would have to provide, if there are n files, you would have to provide the hashes for n-1 files to just validate one file. A Merkle tree does something similar, but with the tree structure. So it uses a binary tree and combines, essentially it assigns every item to a leaf node, and then it takes the hash of those leaf nodes and then combines adjacent leaf nodes to go up the binary tree until you have a single hash. The benefit of this, yes, it does matter where the file is in the tree. So in the image, if you swap L3 and L4, that does matter. And that will result in a different root hash.
How do you know what order you're supposed to do it in?
So when verifying data, you will be given log n hashes and some information about where those hashes are. So exactly what hashes have to be computed. That data is also included. And it'll probably tell you exactly where the file belongs in the tree. All of that is included with the verified data, but all you need, so essentially the point is someone can provide data about the location of the file and the hashes of intermediate nodes and the file itself, and you don't have to trust any of that. All of that can be verified as long as you trust the root hash. So you need this one tiny piece of information to validate the integrity of everything else. Also used, and they allow you to verify the authenticity of a message. A private key is used to sign the message. You can verify the signature by obtaining a message and the signature and providing a key. And the verification process will check that the signature is valid for the message. So it allows people to or proof of authorization. Symmetric key, digital signatures can work on both symmetric and asymmetric cryptography, but I think Bitcoin only uses asymmetric signatures, where the verifier uses a public key and signer uses a private key. Bitcoin is a cryptocurrency. It's that uses a blockchain. Cryptocurrency is a currency that exists essentially completely via an interaction of users and is backed by a blockchain. What I mean by it exists entirely as an interaction of users is that there is no backing authority like a government, like there is for most currencies, and the minting process for new currency is part of the protocol rather than the decision of a central authority. So the control of Bitcoin is decentralized in that everyone has a decision, has a sort of a say in how Bitcoin operates. So the blockchain being decentralized is hosted by anyone who wants to. Usually, if you want to participate in the cryptocurrency, you need to have some copy of the blockchain, because the blockchain is what allows you to verify transactions. But sometimes, for example, it may be impractical to host the entire blockchain on your phone. So sometimes you may delegate trust to another entity, and then that entity will have the entire blockchain. But so the answer to the question is who hosts the blockchain is essentially anyone who wants to participate in the system.
Wait, but if the blockchain gets so big that no one can participate, like what happens then?
The size of the blockchain is a concern, and if it becomes so extraordinarily big that people can't participate, then the natural consequence of that is those people can't participate. But what tends to happen is people re-engineer the protocol so that the blockchain isn't as big, by making it more efficient, or creating ways of operating with not the entire blockchain. Right. So the question of what's stopping one from altering their copy of the blockchain and forging a transaction. Yeah, Teddy's point about large blockchains. So the solution to preventing any individual from forging transactions and altering their copy of the blockchain is something I'll get to in later slides, but essentially it involves using digital signatures and what's called proof of work. So Bitcoin is a decentralized ledger of transactions. Anyone can submit a transaction, and for that transaction to be valid, it has to be signed by the address sending money. Transactions can't spend any more money than an address owns. Anyone can maintain a copy of the ledger. So Bitcoin doesn't exist as a physical coin or backed by anything. The currency itself is a record of payments or transactions between addresses. That is the currency. So you have some starting amount of currency in various addresses, and then those addresses, as they spend and receive money, that essentially becomes the currency. The record of those transactions is the currency and nothing else. And because Bitcoin is decentralized and because of its open nature, anyone can contribute to maintaining the system and participating in it. So long or short positions in cryptocurrencies, I'm reading the chat. Long or short positions are, oh, you're asking me. No. Okay, so Bitcoin is a currency held by addresses. The sort of unit is called, not the unit of the currency, but the unit of item held by addresses is called an unspent transaction output. So the rule of the Bitcoin protocol essentially works by asserting that addresses can create can you hear me now?
Yeah.
Okay. Fun technical issues. Can you see the slides? Okay. Where did I get muted out on? Okay. Right. So, second point. Okay. So, addresses. A transaction is a record that consumes a single UTXO and outputs multiple UTXOs. And each UTXO is sent to a particular address, and you can send a UTXO to your own address. So if you have a very large UTXO, and by large I mean it's an unspent output that contains a large number of Bitcoins, the way you send a smaller number of Bitcoins to another address is by consuming the entire UTXO and then sending back the remainder to yourself as another UTXO. And so these records are signed by the private key of the address. And so anyone with the private key can create transactions for an address, and people without the private key cannot forge transactions. And so all transactions have one input and multiple outputs, with the exception of exactly one transaction per block. And that's the mining reward. It's known as a coin-based transaction. And that transaction has one output and no inputs. And it is essentially the reward for the miner of the block. And I'll get to mining in a moment. And it creates transactions with no source out of nowhere, and the amount that they're allowed to put is dictated by the protocol, and the reward actually decreases over time. So Bitcoin transactions are organized into blocks. So there's a set of transactions that are included into that are grouped, and miners are the ones responsible for doing this grouping. Each block has a header that includes details like the time that the block was created, the hash of the previous block, and essentially a nonce that allows you to validate a proof of work. I'll get into proof of work. But these are all things that define information about the block. And then there's a list of transactions on the block that are included. And so when somebody submits a transaction, all nodes are made aware of it, or all nodes that it's connected to are made aware of it. And then a miner has the opportunity of including that transaction when they go through a process of mining the block. And the hash of previous blocks, by including the hash of a previous block in the header, you prevent reordering blocks without having to recompute every subsequent block. Because if you change the hash in a block, the hash of that block will change, and that change of hashes will propagate down the entire chain. This is important when it comes to computing proof of works. And as a side note, minus the proof of work concept, this chain of hashes is essentially how Git works. When you make a commit, it contains the hash of the previous commit. So in some sense, Git is a blockchain. So the issue is, how can you trust the chain? And this is what the Bitcoin paper written by Satoshi Nakamoto, which is a pseudonym. This is the idea that the paper solved. The difficulties in a decentralized system. Attackers can omit blocks. They can choose not to include transactions in a coordinated fashion, and more importantly, the big problem is that they can alter a previous block in the blockchain. So where this would be a problem in currency, for example, is if you make a transaction for a service or good, and then somebody relies on that transaction being stored and unalterable. If you cannot trust the validity of the chain, then an attacker could essentially remove the transaction after it was made, which would make it unsuitable as a permanent record, and which is essentially what a currency relies upon. Especially when the currency is represents the currency is the record of transactions. So if the transactions are altered, you're fundamentally changing the currency, and I mean, it's just not workable. So the way to prevent this is to create a system where a majority of users, it's not necessarily users, can't alter records, or unless an individual attacker or a coordinated set of attackers represents a majority, they can't alter past records, or it is infeasible to do so. And how majority is defined varies from blockchain to blockchain. On Bitcoin, majority is defined by having greater than 50% of the computational resources of all miners. So Bitcoin uses a method called proof of work to ensure the integrity of the blockchain. Essentially, nodes will trust the longest chain because the assumption is that the longest chain has the most amount of computational work put into generating it. So it takes a certain computational cost to go through the process of mining a block, that is generating a nonce in the block that goes into the header that makes the block valid. And for an attacker to do that work, they would have to, for them to insert a malicious block, they would have to continue creating these malicious blocks after the block that they generated, because if they modify a block, every block afterwards also has to be maintained. So when an attacker presents essentially an alternate chain of blocks with their preferred version of events, they're unable to make it longer than what is the chain that hasn't been attacked, because they do not have enough computational resources to keep up with the generation of blocks by everyone else. So miners are going through the process of generating new blocks, and they're compensated by receiving the output of the Coinbase transaction. There is another thing in here that I didn't put, and that miners are also rewarded by transaction fees that can go in. So when I said transactions include one input and several outputs, part of that input is also sent towards a transaction fee that rewards miners. But essentially, miners are doing a lot of computational work in order to generate what is seen as a valid block. So how does this work in Bitcoin? So there's an assumption that cryptographic hash functions cannot be reversed, and they, like SHA-256, for example, has seemingly random behavior. So one way of utilizing this would be to require someone to find a preimage of a hash. Of course, the problem with this is that is so difficult, no one would be able to do so. So we need some adjustable difficulty, some notion of creating work and then being able to verify it very quickly. So the way Bitcoin does this, if I remember correctly, is they require the first n bytes of the digest to be all zeros. And so miners will try different nonce values until the hash of the block fits this format. And because Bitcoin, or not Bitcoin, because SHA-256 has seemingly random behavior, the best approach to do this is to just guess nonce values until you find a desirable hash. And that takes computational resources as well as time. So I said there were n bytes that have to be a zero, and the reason I used n is because the number of bytes changes based on the total number of miners. If it was fixed and then more miners joined, then blocks would be generated much faster, or as computational resources improve, one attacker would be able to generate blocks, or any individual would be able to generate blocks at an incredibly fast pace. So the way the difficulty is adjusted is the protocol desire or it could be, but a lot of times it's not exactly 10 minutes, but the goal is to make the average approach 10 minutes. So when a new block is added and there's more than 10 minutes between adding that block and the previous, between the time that block was created and the time the previous block was created, the difficulty is lowered. So the value of n in n bytes of the digest that have to be zero is lowered. So you have to search through fewer nonces in order to find a valid hash. And when the time between two subsequent blocks is less than 10 minutes, then the difficulty is increased. So this sort of process attempts to create a stable, essentially tries to make 10 minutes the stable amount of time that the interval that blocks are being generated. And when blocks are right. Someone asked if what happens if you get really lucky and guess once, guess the nonce in, I'm assuming, one try. That could happen, but chances are it won't happen more than once. And with the difficulty that Bitcoin is at right now, the probability of that happening is extraordinarily low. Once you find a valid block, and a block includes the header, the proof of work, and as well as all the transactions, the miner broadcasts out. I don't think so. If people have two different copies of a blockchain because there's a divergence at some point, then they will defer to the chain that is longer. Mining blocks is essentially a random process, so essentially the only controllable factor that you have as a miner is to increase the number of computational resources, and that usually costs money. So that essentially describes the fundamentals of how the blockchain is decentralized but remains unalterable. Bitcoin being the first cryptocurrency was a novel approach to a currency, but there are several issues with Bitcoin that come up. One of them is privacy related, and because there are so many different cryptocurrencies, various currencies have tried to address this issue. So the privacy complications with Bitcoin are twofold. One is that since you can create transactions and addresses without any approval or oversight, it provides an avenue for criminals to technically create transactions without oversight. In the U.S., banks have to comply with various anti-money laundering laws. None of that really applies to Bitcoin as a protocol. The other side of the privacy issue is that all addresses and transactions are public. So if you can create any number of addresses, but if someone associates that address with you, they know every single transaction that you've made and what addresses you've made them to and what addresses you've received them from. All of this is entirely publicly visible, and you can go through the blockchain and view it. There are tools that are made to trace the origins of transactions. There are cryptocurrencies that try to obfuscate this information, like Monero and Zcash, and they can be used for keeping financial records confidential. There's also an additional issue with nodes. So nodes are the individual computers that maintain the blockchain, and they have to have IP addresses of other nodes to connect to. And IP addresses are revealing in some situations, more so than one might want. And so there is an option to actually connect to nodes over Tor. There are other uses that you can use the Bitcoin blockchain for besides just moving money. You can use it for timestamps. Essentially, put a hash of something that you want to show existed at or before a certain time, and when it goes into the blockchain essentially operates as a decentralized source of time. It's not super precise, but because everybody is trying to agree on it, if someone were to present a a ridiculous deviation in the time that didn't match with what every single node in the network was expecting, then they would reject such a block. So there is an unalterability that makes it useful for timestamping and sort of reliability. Also, proof of freshness, as I discussed earlier. You can also use Bitcoin for sending messages, though it's kind of expensive because you have to create a bunch of transactions and transaction fees add up. But you can, and also that message would be public, but it is useful if you want to store that message and make it unalterable, which is essentially the use case for timestamps. There's a list of additional resources. The slides will be posted, as will the talk. Any questions?